Hello guys, how are you today? So today I'll be explaining AP Chemistry Chapter 1. So what do we have in AP Chemistry Chapter 1? We only have 1.1 until 1.4, so basically the full chapter. But I'm going to be explaining section by section. So let us start with the very first section. The first section talks about what? About atoms, subatomic particles, models, what else? About how we deal with subatomic particles, and basically all of this is in chapter 1. So we started in chapter 1 with what? With the definition of atoms. We all know what elements are. Elements are literally the things you see on a periodic table. So all elements are made of what? Are made of atoms. Perfect. All elements are made of atoms. We know that atoms of different elements are different. So if they are from differing elements, then the atoms are different. Whereas atoms of the same elements are the same. So if they're of the same element, they're gonna be the same atom. If they're of different elements, different elements, they're gonna be different atoms. Now this was stated and theorized by who? Theorized by Dalton. He was a physicist or a chemist or both of the above. Now, after we discuss the atoms, we have to discuss something called what? Called subatomic particles, meaning that there's something smaller than atoms. This is the definition of subatomic. Smaller than atom, that is found in the atom. So subatomic particles. Now we have 3 subatomic particles. Now, what was the very first subatomic particle to be discovered? It was the electron. Now, we don't need to know in depth how electrons were discovered, but we need to know who discovered them. Electrons were discovered by a guy named Thomson. Now, we do not need to know why and how electrons were discovered, but we only need to know that Thomson discovered them. What comes after electrons? It comes protons, but protons are so interesting that they need their own page. Okay, perfect. We have their own page. Protons, they were first of all discovered by who? Discovered by Rutherford and his team. His team maybe being his students or his teammates or whatever, but we know that Rutherford led this experiment to discover the protons. Now, how did the experiment go? First of all, we know that Rutherford and his team got what? They got a sample of ores, and they placed these ores in front of what? In front of a thin sheet of gold foil. So they took a sample of ore, and what did they do? They placed it in front of a thin sheet of gold foil. Now, what did they do after this? They decided to study the behavior of the emitted particles. So they started shooting particles of the ore into the sheet. And what did they discover from this? They discovered what? They discovered that some particles, not all, some particles passed through, whereas some deflected, or bounced back. Now, because of this experiment, they created what? They created something called Rutherford's atomic model. So Rutherford's atomic model. Now, how does Rutherford's atomic model go? First thing we know is that we have a cloud of electrons. This is called what? This is called an electron cloud, or just like an electron shell in general. You can have electrons on the shell, electrons inside the shell, and whatnot. And we know that electrons are what? They are negatively charged. But due to this experiment, they were thinking to themselves, how is it possible for some of the particles to pass through and some of them to bounce back? We know that some of the particles, because we're dealing with ores especially, some of the particles bounce back due to what? Due to some particle existing and being there and being like a barrier in between the other side and the ore. But logically speaking, it could not be negative, because if it was negative, there could be a repulsion and attraction. So they decided what? They decided that there were positive subatomic particles were found in the nucleus of the atom. Now this only explains how it's being deflected. But what about the part where it passes through? Very simply, the part where it passes through is what is the space. As you can see, this white inside of the atomic model is called what is called a space. So Rutherford and his team believed that an atom consisted of a positive nucleus and a bunch of electrons surrounding this positive nucleus with a bunch of spaces in between. Now, after Rutherford, someone came and said, this does not make sense to me. And this person, his name was what? His name was, I think I turned on the eraser. His name was Bohr. I think we need a new page for Bohr. Let's open a new page. His name was Bohr. And what do we call this? We call this Bohr's model. Bohr stated what? He stated that electrons should be assigned specifically, because for them to just be existing randomly, they may like repel each other and they may be attracted to the nucleus and they may be moving in random motion, which will make the atom very weird. So Bohr stated that electrons are assigned specifically. And how are they assigned? Again, he will follow Rutherford's model, and he said that we have a positive nucleus in the middle. And then what do we have? We have the first shell, a second shell, a third shell, and so on and so forth. Why did he say this? He said because each shell can assign a specific amount of electrons. So each shell can assign a specific amount of electrons. Now, after Bohr's model, Pauli came. There's a guy, his name is Pauli. He came and he stated that electrons in the same atom can exist at a certain level of energy. That means some electrons require a specific amount of energy, which is maybe more or less than the other electrons that are all in the same atom, right? So Pauli proposed what? He proposed that electrons, E minus, in the same atom can exist at certain levels of energy. Now I'm gonna say two extra sentences, very important. I'm not gonna write them, please pay attention. What are these two sentences? First of all, these energy levels are described by quantum numbers, right? And we also know that no two electrons in an atom can have the same set of quantum numbers. So no two electrons can have the same energy value. So to add an electron will require maybe more or less energy than to remove another or to add another electron. So like let's say I want to add one electron, maybe it will take me 5 joules. Then to add another electron, maybe it will take me 100 joules. So these are different energy levels depending on adding or removing electrons. So this was Pauli's concept or Pauli's principle. Now we move on to another scientist. These are we have a lot of scientists. This scientist, his name is Schrödinger. Okay, this is how we spell it. He stated that maybe shells or orbits of electrons. So let's go back to Bohr's model. As you can see in Bohr's model, he drew a bunch of shells, and he said that each shell can assign a specific amount of electron. But then Schrödinger came and he said that electrons carry a specific amount of energy, the same thing as what Pauli said. And he said that they move about the nucleus in a cloud-like region. So they're moving in a different way than how Bohr explained it, because Bohr explained it that they're moved in fixed orbits, whereas Schrödinger is saying that they move about the nucleus in cloud-like regions. So Schrödinger said that electrons carry a specific amount of energy and move about the nucleus in cloud-like regions, and not, keyword is not, in fixed orbits. Perfect. So then, after all of these discussions and ideas and concept, Rutherford, he's back with his team, he's back with his students, and then he's doing what? He's measuring the number of particles in the nucleus. And he says that there's definitely way more particles in the nucleus than protons. So he's saying that there is more particles in nucleus than only protons, right? So Rutherford found that there's more particles in the nucleus than only protons. But what's the thing? The thing is that these particles are not affecting, because we know that we have a positive charge, which is protons, and a negative charge, which is electrons, and they will balance each other out. So if there's more particles in the nucleus and they're not affecting the relation between the positive and the negative charge, then he said that they do not have a charge. Do not have a charge. And from this, he made up the term what? He made up the term nucleus. And, not nucleus. He made up the term neutrons. And from this term, neutrons, he was able to say what he was able to say, that protons, which is positive charge, plus neutrons, which is no charge, is equal to what? Is equal to all of the nucleons in the nucleus. Alright, perfect. So now we discussed how each of the 3 subatomic particles were discovered. So what are the particles, first of all? What is their symbol? What is their relative charge? And what is their relative mass? So the very first subatomic particle we have is what? Is proton. Okay? Or actually, let's start with the first one that was discovered, which is what? Which is the electron. The symbol of electron is what? It is E minus. Electron has a relative charge of -1, and it has a relative atomic mass of 1 over 1836. Now we will see why this is very, very important. Then we'll move on to the second one, which is the proton. Proton, its symbol is P+. It has a relative charge of +1 and a relative mass of 1. And then last but not least, we have what? We have the neutron. It has a symbol of N0 because it does not have a charge, a relative charge of 0, and a relative mass of 1. Now, why did I say this was gonna be very important? Let us first of all sketch a diagram. Let us say we're dealing with an electric field, and we have a positive side over here and a negative side over here. And what do we shoot? We shoot an atom, right? We are shooting what from here? We are shooting atoms. We know, first and foremost, that we have 3 different types of subatomic particles in the atom, right? The first subatomic particle we have is the electron, and the electron is going to deviate like this. After I draw, I'm going to explain why. The second one we have is the proton, and the proton is going to deviate like this. And last but not least, the last one we had was the neutron, and the neutron is going to deviate like this. Now, why exactly is this? First of all, we'll go back to electrons. We know that electrons, what? They are the lightest particle. They have the smallest relative mass. So because of this, they're gonna what? They are gonna deviate the most. Another thing we noticed is that this is the positive charge and electrons are negatively charged. So positive and negative, what do? They attract each other, whereas negative and negative, they repel each other. We move on to the proton. Proton will deviate, but they will deviate less. Now, what do we also notice? This is negative and this is positive. So positive and negative attract, positive and positive repel. Last but not least, there is no deviation. It does not change the motion. Why? Because it's not attracted to either positive or negative. It has no charge. So it's not attracted to this, it's not attracted to this, and it's repelled from either. I'm sorry, it's not repelled from either. So this is now like the basis and definition of subatomic particles. After this, we'll move on to what? We'll move on to the representation of an element. We first start with X. X is what? X is the chemical symbol of the element. Then, what do we have as well? We have on top A, which is the mass number. And then we have on the bottom, what we have on the bottom, Z, which is what? Which is the atomic number. All right, perfect. Now, atomic number we know is the same as what? The same as the number of protons. Now, let us say that we did what? That we are dealing with what? We're dealing with an atom. In the scenario that we're dealing with an atom, the total charge is supposed to be equal to 0. Why? Because the protons are supposed to be equal to what? Are supposed to be equal to the electrons. So let's take an example. Let's take an example that we have. Let's take two examples. Let's say we have Na, sodium, which has a mass number of 23 and an atomic number of 11, and oxygen, which has a mass number of 16 and an atomic number of 8. Let us see how many protons it have and how many electrons it have. First of all, this is the number of protons, 11. And because it's an atom, we're dealing with an atom, it's supposed to be 11. Why? Because plus 11 minus 11 is equal to 0. Same thing with oxygen, 8 electrons, because plus 8 minus 8 is 0. Now, what happens if we decided to do what? If we decided to take an electron away or add an electron. So it's either you're taking away an electron or you're adding an electron. Let us take the same examples again. Okay? We have Na and we have O. Na is 23, 11. O is what? O is 16, 8. طيب. If you remember from before, cations are when we lose electrons. That means we're taking away electrons. Let us say, of course, you're supposed to know that sodium will turn into a cation. So we'll take away an electron from sodium, and what will happen? It will have 11 protons, and how many electrons? And 10 electrons. So 11 minus 10 is 1, so it will have a charge of plus 1. Now, oxygen, you know that it becomes O2 minus. So oxygen has 8, and you added what? You added 2 electrons, so it becomes minus 10 now. 8 minus 10 is minus 2, so it becomes what? It becomes O2 minus. This is how you are supposed to deal with it. And just like that, what did we finish? We finished section 1.1. Now we will move on to section 1.2. Now section 1.2 is shorter than 1.1. It just discusses isotopes. So first thing we need to define is what is isotopes. Isotopes, let me zoom in a bit. Isotopes, in order for two atoms to be an isotope, they should be of what? They should be of the same element. They should be of the same atomic number, that means the same number of protons, and they should be what? They should be of the same charge, and they should be what as well? They should have a different mass number. Now, when you look at this, same element, same atomic number. When they have the same atomic number, then directly you related that they will have what? They will have the same chemical properties. Now, they have the same charge, but they have what? A different mass number. When they have a different mass number, you relate it directly to what? That they have different physical properties. Okay? Now let's take some example of isotopes. Let's say we have hydrogen over here. So this is the atom of hydrogen, and we have a positive nucleus only. Okay, so it's gonna be what? It's gonna be hydrogen 1 because it has only one proton, and 1 because it only has one thing in its nucleus. Then let's say we draw another one. We now have what? We have P plus and N0. and surrounding it is the electron shell. It becomes what? It becomes H. It has the same number of protons, which is 1. But now how many particles do we have in the nucleus? We have 2 particles, so H21. And let's say we did now 1 proton, another neutron, and another neutron. So it's gonna be hydrogen with 1 proton, but 3 particles in the nucleus. This is very simply the definition of isotopes. Now, we can say that they're gonna have what? The same element, same atomic number, same charge, same chemical properties, but different mass number and different physical properties. Now we move on to a very, very, very important concept, which is known as the relative isotopic mass. What is the relative isotopic mass? So the relative isotopic mass is very simply what? It's very simply the addition of a mass multiplied by its percentage to another mass multiplied by its percentage. So let's say you have the mass of isotope 1, right? Mass of isotope 1, mass 1. And you have its percentage abundance, which is percentage 1. Okay? Or you can take it as number n1. This is percentage abundance. Then what do you also have? You have mass number 2, or you have percentage 2, and you have, for example, abundance 2. How do you find the relative isotopic mass? Very simply, it's gonna be mass 1 multiplied by percentage plus mass 2 multiplied by percentage. This is percentage 1, percentage 2. You can either do it like this, or you can do it how? You can do it mass 1 multiplied by n1, which is the abundance 1, plus mass 2 multiplied by abundance 2, all of it over what? Over 100. In my opinion, I prefer to use this way. If you want to use this way, of course, you can use this way. Now, of course, scientists are not gonna be wasting their time on taking an atom and finding whatever this is and whatever that is. So they use a device called a mass spectrometer. What does a mass spectrometer do? It is used to measure the masses and abundance of given isotopes in a given sample. Okay, we don't need to know how it works, we just need to know that a mass spectrometer is used to measure the masses and abundance of given isotopes in a given sample. Now, what could they do in the exam? In the exam, they could give you a graph, and this graph looks like this, right? What do we have over here? We have the mass number over here, and we have the percentage over here. The maximum percentage is 100. Okay, so this is what the relative abundance, RA. And what do we call this graph? We call this the mass spectrum graph. Okay, now what happens exactly? They will give us values. For example, a value here, a value here, a value here, a value here. Or let's make this one smaller. A value here, and a value here. So they could give us graphs like this, right? And they will give you masses. Let's say you have mass 1, mass 2, mass 3, mass 4, and mass 5. And for each of the masses, you have what? You have a relative abundance. So we're going to call this N1, N2, N3, N4, and then last but not least, N5. Now, what could they possibly ask us from this graph? They can possibly ask us 3 questions. First question is what? Is the number of isotopes. Of course, in this graph, how do you count the number of isotopes? You see 1, 2, 3, 4, and 5 graphs or 5 lines. So this means there's 5 possible isotopes. Then they will ask you for the, the relative isotopic mass, RIM. Again, how is my bad? How is this found? It is found by mass multiplied by percent abundance, right? It's the summation, let's say, the summation of mass multiplied by percentage abundance. So in this scenario, how would we find it? We would do mass 1 times N1 plus mass 2 times N2 plus mass 3 times N3 plus mass 4 times N4 plus mass 5 times N5, and all of this is over what? Over 100. Or you can do mass 1 times percent 1 plus mass 2 times percent 2, and etc. so on and so forth. And the last thing they will ask you for probably is what? The last thing they will probably ask you for is the element. So how do you find this? after finding the relative isotopic mass, you will look to the periodic table and you will see which element has this mass or approximately this mass, and you will choose it. Just like that, we finished what? We finished 1.2. Now we'll move on to a new section, which is 1.3. I believe 1.3 and 1.4 are the bigger section. So 1.3 is the biggest chapter in all of this, okay? So what happened? Scientists in chapter 1.3, they're telling us that scientists were discussing the nature of light. So we have something called light. And scientists were discussing its nature. They thought that light were what? They thought that light was, or were, let's say light was, they thought that light was streams of particles. So initially, let me move this, I don't like how it's situated. So first we'll start with what? We'll start with the first idea they thought. They thought that light was streams of light, of particles, my bad. So light was streams of particles. Until who came? Until a second person came, and this person, his name is James Maxwell. So let's write him here to give him credit, because he already has credit, but as well, he came up with this theory, he finalized this theory after 200 years. And it's because of him we believe that light also has a wave nature. So James Maxwell, what did he say? He said, I did some experiments and other people did some experiments, and all of this proves that what? All of this proves that light is a wave. So James Maxwell stated that light is a wave. And what did he call this wave? He called this wave the electromagnetic wave. So light is a wave called electromagnetic wave. Perfect. So now we're going to stop here. We're going to leave this page and we will come back after. Okay? Let us do a quick definition of what? Of electromagnetic radiation. Electromagnetic radiation. Electromagnetic radiation, very simply, is what? Is a form of radiant energy that has wave-like characteristics. Very simply, this is proving what? This is proving Maxwell's theory or Maxwell's statement that it's a radiant form of energy that has wave-like characteristics and travels in vacuum at the speed of light, which is 3 times 10 to the power of 8 meters per second. Now this is all electromagnetic radiation, and regarding electromagnetic radiation we have 3 values. Lambda, which is the wavelength. Of course, we learned this in physics. If you guys don't know this, this is a very big issue. So wavelength, which is what? Which is the distance between 2 peaks or 2 troughs. Then we have V, they used a different notation. V, which is the frequency. Frequency is what? Frequency is the number of waves that pass per second. And then finally C, which is what? Which is the speed of light in vacuum. Which is what? Which is 3 times 10 to the power of 8. Now we did not write their units. Why? Because specifically we will write them now. Wavelength is always in meters. Frequency is always in hertz, and then speed of light in vacuum is always in meters per second. Now, of course, if you guys don't know this equation, then I don't know how you guys are passing in physics. So this equation is what? This equation is C is equal to lambda V. Or in physics, it's what? It's C equals lambda F. But in chemistry, because we're in chemistry now, not physics, I love how everything is the same in math, physics, chemistry. It's all the same concept, guys. We have what? We have that the speed of light is the wavelength times the frequency, or C equals lambda V in chemistry. In physics, please don't mix up. In physics, it's C equals lambda F, okay? And we also gave all of their unit. I love how scientists like to mix us up a lot. Because now you're gonna see another equation. Let me see when. Oh, I think in 1.4 you'll see the equation. Yeah, in 1.4, is it? No, my bad. Not in 1.4. Very soon, though, you're gonna see an equation which will, also is related to physics, but it's different because this is chemistry. Chemistry likes to overcomplicate everything. But if it wasn't for chemistry, we would not be able to find out what is in atoms and what composes us and how do things react and whatnot, you know? So now, this, of course, you guys need to have it memorized. If you don't have it memorized, it's another big problem because this is, again, from physics. Okay, what do we know? We know that radio waves, then microwaves, then visible light, then, oh, sorry, my bad, then infrared, then visible light, then ultraviolet, then, I don't think there's space. Whoops. Let's make the arrows shorter. Radio waves, then microwaves, then infrared, then visible light, then ultraviolet. Then after ultraviolet, what do we have? We have X-rays, and after X-rays we have gamma rays. Perfect. Okay, so now you need to know what each one is used for. Of course, some of them we know them from physics, but here in chem there's something different. We know that radio waves work in what? They work in radios and TV. Microwaves, they work in the microwave. But how do they work? They take the molecules, especially molecules of water, and they rotate them. This rotation causes heat because there's energy, right? It causes heat, and this heats up the food. So it rotates molecules. Now, infrared, what does infrared do? It emits energy, it emits heat. So what does it do as well? It vibrates molecules. Visible light and ultraviolet both fall under the same category where they do what? They do electronic transitions. So, radio waves do radios and TV. Microwaves are, they rotate molecules. Infrared, vibrate molecules. Visible light and ultraviolet are, they do, electronic transitions. And then finally, X-rays and gamma rays, what do? They do ionization. So this is all you need to know, other than the fact that as we go down in this scenario, as we go down, the wavelength decreases, but the frequency increases. Okay, perfect. This is literally all you need to know. Now we move on to a next concept, which I think we all have seen at the beginning of the term, which is what? Which is Planck. What did Planck state, and why is he important in chemistry? Planck stated that energy, like energy in general, can be quantized, meaning it can have a quantity. And they come in packets. So they're not single particles of energy, they come in packets, right? So what did he say? He said that energy can be quantized and comes in packets. Perfect. What do these packets do now? Or what did he call these packets? He called these packets a quantum. Very simply, this is what Planck stated, and he called them a quantum. And because of this, Planck got what? He kept on solving and solving and solving, and he kept on getting a same constant. And this constant is denoted by h, and it is what? It's 6.626 times 10 to the power of minus 34 joules per second. Or joules times second, not per second, joules times second. Now, where exactly did he get this constant from? He tried to do what? He tried to take the energy, and he tried to divide the energy that he got by what? By the frequency of what? Of the wave. So the energy is always in joules. This energy is either absorbed or released. The frequency is always in hertz, or it can be in 1/second. And from this, he was able to get his constant. So what did he say the equation was? E energy is equal to his constant multiplied by what? Multiplied by the frequency. Now, what can we notice? Because his constant is constant, right? It will not change. If something increases, it's going to stay the same. It's constant. But because his constant is constant, if we increase the energy, then the frequency is going to increase. But if we decrease the energy, then the frequency as well is going to decrease. So we can say that the higher the energy get, the higher the frequency is. The lower the energy get, the lower the frequency is. This is why gamma rays are the most energetic particles, because they have what? They have the highest frequency. Perfect. That's Planck explained. Now we need to go back up all the way over here. So we first said that light waves were said to be streams of particles, but then James Maxwell corrected, and then comes the infamous or the very, very famous what? The very famous Einstein. What did Einstein do? He suggested. What did he suggest? He suggested what? He suggested that in addition to waves, he suggested that in addition, this means plus, to waves, light also consists of particles. Light also consists of particles or bodies or photons. We can say bodies or photons. Now, how is Einstein proved correct? Einstein is proved correct by something called what? By something called the photoelectric effect. Very simply, what is the photoelectric effect? What is the photoelectric effect? The photoelectric effect, basically, is when they got a metal surface and they expose it to light, they will notice what? They will notice that electrons are being emitted. But this light has to have what? It has to have a minimum frequency called a threshold frequency. So before we continue, let's write what we stated. We stated that the surface of a metal emits or shoots electrons when it is exposed to what? When it is exposed to light of a minimum frequency called what? Called the threshold frequency. Now, what exactly is this threshold frequency mean? This threshold frequency means that it's the minimum energy that photons should strike with to allow what? To allow the electrons to overcome the attractive forces that hold them in the metal. So the threshold frequency is the minimum energy that photons should strike with to allow the electrons to overcome the attractive forces that hold them in the metal. Now, all of this explains what? All of this explains a new rule which is used nowadays, which is the definition of light waves nowadays, which is what? Which is the dual nature of light. It is what? It is corpuscular and what? And wave-like. Perfect. Now we need to go back to something we discussed at the beginning of the video, which was what? I think it's over here, which is Bohr's model. Here we go. We need to discuss now what? We need to discuss Bohr's model. Let's say we have what? We have two atoms. Right? We're gonna call it the nucleus. Let's say the nucleus is positively charged. It is positively charged. And then this has 1, 2, and 3 shells around it. Not the best at drawing shells. And this has 1, 2, and 3 shells around it. Where do you think the interactions will happen? Will they happen between this shell and this shell? Or these electrons? Or between these electrons? Or between these electrons? Or between these electrons? Or between the nucleus? Definitely it will happen between what? Between these two electrons, these two shells. Now, what do we call these two shells? These two shells, instead of saying electron shells, what do we call them? We call them what? We call them energy levels. Now, one thing we should agree on is that electron shells and energy levels, what do they refer to? They refer to state of energy of electron and not its location. So neither electron shells nor energy levels refer to the location of the electrons. Instead, they refer to the state of energy of the electrons. I think I meant to say, I think I messed up before. So I mean to say they don't refer to the location of electrons, they refer to the state of energy of electrons. Now, electron shell is the shell, right? But energy level, on the other hand, I don't know if my arrow will continue here. Energy level, on the other hand, what is its definition? Energy level, what does it do? It assigns a positive integer n, known as what? This is back to Pauli's theory, known as principal quantum number. Okay? So it assigns an integer n known as the principal quantum number, and this n, this positive integer n, it indicates the average distance. This is average distance of the electron from the nucleus. In addition to what? I think I need a different color for this. I love to use colors, they're so nice. So it indicates the average distance of the electrons from the nucleus, in addition to what? In addition to the energy possessed by the electron. So now we've been discussing too much about the structure and the shape and whatnot of the atom. But now let's actually talk about the atom itself. The atom itself has states, and it has how many states? It has 2 states. It has a ground state, and it has what? It has an excited state. So what is the definition of a ground state? The ground state, in other terms, is known as the lowest energy level an electron possesses. Whereas the excited state is a temporary condition in where what? In where if enough energy, so I think we need more space for this. I'm just gonna zoom in. It's a temporary state in where if enough energy is transferred to an electron. So if enough energy is transferred to an electron, what does it do? It moves the electron to a higher energy level n. And because it moves to a higher energy level n, it becomes excited. So let's look at these two and let's compare. Ground state, which means it's calm, is at the lowest energy level an electron possesses. So it can be at the lowest energy level possible. Whereas in the excited state, it's when a random energy comes, and this is temporary, of course. A random energy comes, and it will transfer, of course, if it's strong enough, it will transfer the electron to a higher energy level. And if it's at a higher energy level, then it's not at the lowest energy level for sure. That means it's going to be what? It's going to be in the excited state and not in the ground state. Now, what do? We go back to our equations which we learned, which is E is equal to HV, and C is equal to what? C is equal to lambda V. Now, what did Planck do? Planck decided, you know what? Let's not overcomplicate everyone's life. And he said, let me make an equation. Instead of people putting it in this and then having to re-put it in this, what did he do? He took V alone. He made V the subject. So V is equal to what? It's equal to the speed of light over the wavelength. And he said, what happens? Like, very simply. What happens if I would substitute V over here? He said it's going to be E is equal to H times C over lambda. Oh my goodness, it's a new equation. Even though it's the same exact thing, but it's a new equation, which is basically the expanded form of what? Of Planck's equation. We're going to write in big red, expanded. All right, perfect. So now we discussed what? We discussed energy levels and we discussed the states of the atom itself. Now let us discuss how and why do they discuss this and how do they prove that there is the presence of electrons in energy levels. Now this is going to require an experiment. I think you guys can do it with me. So how to prove presence of electrons in energy level. So very simply, let's take a break for a second. Take a clear ruler, take your phones, or like a flashlight if you have anything. I'm gonna take my phone. I will take my phone, I'll turn it on, and I will take my ruler and I will go to a wall. I have a wall right next to me over here. So I will put my flashlight to the ruler, and I'll try to move my phone as far as possible as I can from the ruler. And what I see, I don't know if you guys can see that, I don't see you, but what I see is that under, or like above, it depends on how I flip my heyday, but actually both above and below, but above and below my ruler, the reflection, what's it called? The shadow of my ruler, I can see what? I can see a rainbow. I can see a bunch of colors. Alright? So this proves what? This proves that there are electrons in the light that I'm shining from my phone, or like the light you're shining from your phone, that when it passes through the ruler, what happens? It will be like spread, and this will show what? This will show the energy levels. So each color presents a different energy level. Now let's say you want to do this experiment on a larger scale in the lab. Now let's say again you wanted to do this experiment on a lab scale. You have two different ways of doing it. The first way is using a regular source of white light, like for example the flash in our phones. So what happens? We basically have a positive negative terminal. We have a light bulb over here. And this also comes back to physics again. We will have what? We will have a slit over here, or a plane, right, with a slit. And then we will have what? We will have a prism over here. Let's draw the prism. And we will have a prism over here. So basically, look what happens. Yellow is going to be the color of the light. The light will come here and here. It's unpolarized. I don't know if you can see this color. And then it will become polarized from the slit, and it will go into the prism. And then after going into the prism, where does it go? It will go on a screen over here. And then from the prism, what happens to it? It will diffract into all colors. So it can diffract from red, let's say, over here. And then in the end, purple over here. And what colors do we have in the rainbow? After red, we have orange. After orange, what do we have? After orange, we have yellow again. Of course, it's supposed to be white light, but I cannot represent white light on a white screen. Then after yellow, we have green. Then after green, we have blue. And then finally, after blue, we have indigo, I think. Just something like this. And then we have what? We have violet. So the unpolarized light will go into the polarized light into the prism, and then it will turn into the colors. Now, what do we call this spectrum? We call this a continuous spectrum because it's just continuous colors. Now, the second experiment you could do, we have an experiment B, we will call it, is if you do the same exact thing, but instead of a light bulb, you have what? Instead of a light bulb, you have a hydrogen discharge tube. So this over here is minus plus. It's called a hydrogen discharge tube. Same exact, like literally same exact concept as the one above. We're gonna have a slit, right? And what's after the slit? We have a prism. Let's make this color for the prism. We have a prism, right? And then what happens? We have light. Light will come from the hydrogen source. It will come into the slit. The slit will change it from unpolarized into polarized. And then it will pass into the, into the prism. And here's the difference. Here is the difference. Look what we're going to have. We're not going to have all the same colors. We're going to have maybe like red, then purple, then green, then blue and whatnot, but we're not gonna have all of the colors, and then they're not gonna be continuous. Here they're supposed to be connected to each other, but I just drew it like that to show you. But here they're gonna be separated from each other. And what do we call this? We call this a hydrogen, not a continuous, a hydrogen spectrum. Now, I forgot to mention, how does the light come out of a hydrogen discharge tube? Very simply, under a very high voltage, the H2 bonds are going to break, right? And when they break, they will become very excited. Why? Because they gain the energy, so they will be pushed from a lower energy level to a higher energy level, so they become excited. And when they're excited, they will release what? They will release visible light. I've been on this video for like almost an hour, and I still have 5 pages left. I'm very happy. Like 5 pages left in my notes. So let's move a bit faster now. Now, for the equations, for the maximum number of electrons in an energy level n, it is what? It's equal to 2n squared. But for the maximum number of orbitals, now we will see what orbital means. In an energy level n, it is what? It is n squared. Now, let us discuss the definition of an orbital. Of course, we know what energy levels are, okay? But what is in each energy level? Each energy level consists of what? Consists of one or more sub-level. And what are these different types of sub-level? We have S, P, D, and F. Not all of them have P, D, and F, but all of them are supposed to have what? They're all supposed to have S. Okay, that's why we say that energy levels consist of one or more different what? Sub-levels. We call these sub-levels or sub-shells. Now, what do the sub-levels hold? Sub-levels consists of one or more orbitals. So what do we have? We said we have S, P, D, and F. We have S. S has only one orbital represented by one box. But now, what? S is represented by one box. But I'm going to separate it into two because we have two different ways of drawing. Then we have P, which is a big box. Right? Then we have D, which is an even bigger box. Then we have F, which is quite literally the biggest box ever. I'm trying to make it big, okay? Now what happens? S only has one orbital. And we know that each orbital fits how many electrons? It fits 2 electrons. That means it's supposed to have one electron and another electron. But why do we put them like this? We put them like this because they are supposed to be two opposite spin pair of electrons. They should be moving in opposite spin. If they're not moving in opposite spin, then you did something wrong. You can represent it as one up and one down, or you can represent it arrow up or arrow down. Now we move on to P. P has 3 orbitals. So each P has 3 orbitals. You can represent it by one up, but how do you fill the P subshell? You start by filling one that's spinning up, one that's spinning up, one that's spinning up, and after you fill all of the orbitals with one that's spinning up, you can fill one spinning down, one spinning down, one spinning down. Now, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. Same exact thing for the D. D, however, has 5 orbitals, so each D has 5, so that's 1, 2, 3, 4, and 5. I don't know how I'm gonna fit them. Let me fix it a bit. 1, 2, 3, 4, and 5. Then 1, 2, 3, 4, and 5. So we're gonna have what? 1 up, 1 up, 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, 1 down, 1 down. Then 1 up, 1 up, 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, 1 down, and 1 down. We always have to fill them first with the up, and then we can start with the down. And now last but not least, what do we have? We have the F, which consists of 7 orbitals, so this is going to be a bit tricky. 1, 2, 3, 4, 5, 6, and 7. And then 1, 2, 3, 4, 5, 6, and 7. So 1 up, 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 1 down, 1 down, 1 down, 1 down, 1 down, 1 down, 1 down. Or 1 up, 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 1 down, 1 down, 1 down, 1 down, 1 down, 1 down, and 1 down. So that leads us to our last and very last, actually, final point of chapter 1.3. Alhamdulillah, now I still have 1, 2, 3, 4 pages left to explain. Which is just like a summary of SP and DF orbitals. So S, we need a small space. P, we need an adequate space. D needs the largest space, and then we have F. Now, what do we need to write as well? We need to write the maximum number of electrons, the maximum number of orbitals, and I think we also need to write S, P, D, and F. You know what? It's not going to fit like this. I'm just going to write, first of all, this is S, right? And S is what? S is a circular spherical shape. For the maximum number of electrons, it's 2 maximum. The maximum number of orbitals, it's 1. And last but not least, the starting energy, or like energy level, EL means energy level, or N, my bad. The starting N is what N has to be greater than or equal to 1. So starting from 1 and forward, it's S. Now we move on to the next one, which is what? Which is the p orbital. The p orbital has one specific shape, which is a dumbbell shape. So it can be like this, it can be like this, it can be like this even, can be like this, as long as it's a dumbbell shape, right? It has a maximum of 6 electrons and a maximum number of 3 orbitals, and its starting energy level is 2, so anything greater than or equal to 2. Now we move on to D. D is the biggest one because it's what? It can be a clover shape, which is like this, or it can be like this, or it can be like this, you know? So as long as it's a 4-leaf clover shape, and there's an additional shape, which is like this, which is what? Which is a dumbbell, which is the same shape as P with a donut in the middle. It has a maximum of 10 electrons, maximum of 5 orbitals, and N, it starts at 3, so anything greater than or equal to 3 works. Now last but not least, we have what? We have F orbitals. We don't have to take any of their shapes, but we know that they have maximum of 14 electrons, 7 orbitals, and N is greater than or equal to 4. And just like that, alhamdulillah, we finished what? We finished 1.3. How many pages did 1.3 take? I don't know, but it took a lot of pages. Perfect. Now we move on to the very last section, which is what? Section 1.4, which is basically what? Which is basically electron configuration. There are 3 rules regarding electron configuration. The first rule is the off-bow rule. The second rule is Pauli's exclusion rule. Exclusion. Pauli is very important when it comes to these, by the way. And then the last one is what? It's Hund's rule. Now what does the off-bow say? The off-bow says that electrons tend to occupy the lowest orbital, or the lowest energy level, energy orbital, my bad, the lowest energy orbital first. Perfect. Now, this is the off-bow principle. Then what does Pauli's exclusion say? Pauli's exclusion says that orbitals can be occupied. I think we need more space. I don't think it's gonna fit. Let me just make this a bit smaller. Okay, how do I make it smaller? Can I make it smaller? I doubt I can make it smaller, but I'll move it a bit up here. Okay. I don't know, it's bugging me. Let's take back everything to how it was before. Let me just take all of this and we move it up here so we can have space. It's okay, guys, you're gonna struggle with me a bit. Wait, hold on. I'll just move this here because we're done with it, okay? Then, what's the second rule? The second rule is that Pauli's exclusion rule is that orbitals can be occupied with a maximum of 2 opposite spin electrons. Okay? So off-bow states that electrons tend to occupy the lowest energy orbital first, whereas Pauli's exclusion states that orbitals can be occupied with maximum, there's no exceptions, a maximum of 2 opposite spin electrons, meaning it's either like this and like this, or like this and like this. So we finished with this. Let me get rid of this now. Goodbye. Now, the last thing we have is what is a Hund's rule. Hund's rule is very, very, very important. It's the rule that we were dealing with over here, where I said you do one, then one, then one up, then one up, then one up, then one down, then one down, then one down. This is called Hund's rule. He states that orbitals of equal energy or of the same energy are first occupied by a maximum number of unpaired electrons having the same spin. So if you have the p sub-level, you're gonna have 3 orbitals in it, right? So these are called what? These are called degenerate orbitals. Why? Let me just explain it here. We have P, right? P is a big box. It has 1, 2, 3. This is Px, Py, Pz. And let's say this is 2p, right? So it's gonna be 2px, 2py, 2pz. These are called degenerate orbitals. Why? These are called degenerate because they have what? They have the same energy level and sublevel, same energy level, which is what? Which is principal quantum, PQ, and sublevel, which is also referred to as subshell. So 2px is equal to 2py is equal to 2pz. Why? Because they have the same energy level n and the same sublevel, which is p. Right? Now, because they are equal, they have what? They all have the equal energies, right? Hund said that you have to occupy first by the same spin, which in my opinion, it's better to start with up. So 1 up, 1 up, 1 up. Then you go 1 down, 1 down, 1 down. And these are just the electronic configuration rules. Now let's explain the off-bar a bit further. Off-bar, he said, let us order the electronic configuration in this method. You first start with writing 1s, and then 2s, 2p, and then 3s, 3p, and then 4s, 4p, I think 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f, etc. So on and so forth, right? What is the off-bar rule? Off-bar rule states that odd, you're gonna add 1 sub-level to it, whereas even, you're gonna take the same sub-level, right? What does this mean? This means we started with 0 sub-levels. This is the first line, right? So it's an odd number, meaning we will need to add 1 sub-level to it. So we will draw an arrow like this. The second one is what? The second one is an even one. So it's gonna take how many sub-levels? It's gonna take 1 sub-level. Why? Because even will take the same number of sub-levels as the one before. Now it's odd. It's the third one, right? The third arrow. So the third arrow is odd, so we'll need to add 1, so that's now 2 sub-levels. Then fourth arrow is even, so you're gonna take 2 again. Fifth one is odd, you're gonna take 3 now. Sixth one is even, so you're gonna take 3 again. Seventh one is odd, so you're gonna add 1, you're gonna take 4 now, and then so on and so forth. This is basically off-Bar's law. Now there is another method my teacher taught me, which is you write S, and then you start writing backwards. P, S, P, S. And then D, P, S, D, P, S. And then F, D, P, S. F, D, P, S. And now what do? You should know that S can hold maximum of 2, P can hold maximum of 6, D can hold a maximum of 10, and then F can hold a maximum of 14. Okay, and then you start labeling. We know you start with the first energy level for S, which is 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. Then you start with P. It starts at the second energy level, so 2, then 3, then 4, then 5, then 6, then 7. Then you start from D. It starts at the third energy level, 3, then 4, then 5, then 6. Then you start with F. It starts at the fourth energy level, 4, then 5. Now, of course, if you want to do extra, I'm gonna write with the recorder pen. You can put 2 here, 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 and 2 here. And then 6, 6, 6, 6, 6, 6. My bad. I'm not focusing. 6 here. And then 10, 10, 10, 10 here, and then 14, and then 14. You can do it like this, but it's up to you. You can use either ways. Now let's do an example of electronic configuration. Let's see, let's choose a color, nice color. Yeah, my pen. Here we go. Let's choose a nice color, and let's choose a nice one. Honestly, I don't know why my favorite element for some reason is sodium. Okay, sodium is what? Sodium is 2311. So let's do the electronic configuration of sodium atom. We first start with 1s2. You go back. You finished 1s, you cancel it. You cancel it. Then 2s2. You cancel it. How many is that? That's 4. Then 2p6. How much is that? That's 10. Then 3s. You will remove it. But 10, how many do we have? We have 11 electrons, so it's supposed to be 1 over here. This is how you do the electronic configuration. Now, there's another term called shorthand configuration, in which what do? We go back to our periodic table. We will see, okay, sodium is in the 3rd period. So I will look where? I will look to the noble gas before, the noble gas of the 2nd period, right? It's neon. So what do? I will write neon. Now neon has what? It has an atomic number of 10. So that means we will remove 10 electrons and we'll be left with what? We'll be left with 3s1. This is the shorthand electronic configuration. Okay, now of course to everything we have exceptions. Here I do recommend that you memorize the exceptions. There are only 2, which is chromium 24 and then copper 29. Their configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Now, what's the problem in this scenario? In this scenario, it will not work out like this. So what did they do? They said 4s1 and 3d5. So this is the only exception for chromium, right? You take 1 electron for the 4s2 and you put it in the 3d. Perfect. Okay, perfect. Now for copper, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. Again, they're facing the same problem. So what did they do? They took 1 electron from the s and they gave it to the d, so now it's 10. Okay, so these are just the exceptions you need to memorize. Now, of course, everyone knows, hopefully everyone, they know what the definition of valence electrons are. Valence electrons are very simply what? They are electrons that occupy the valence shell of outermost, valence shell or outermost, this is R, or the outermost occupied energy level of an atom. So valence electrons are what? They are electrons that will occupy the valence shell, which is the last or outermost occupied energy shell of an atom, right? When valence shell is full, we say the atom has noble gas configuration. Noble gas configuration. Perfect, perfect. Now, we discussed how to do the configuration. So we were doing the electronic configuration of atoms. Let us now do the electronic configuration of ions. Let's take my favorite element for some reason, sodium. Sorry, there's a paper on my, something on my screen. Sodium, and we take it as an ion. That means what did we do to it? We removed an electron. Perfect. So we're gonna just do the regular configuration of sodium 11. So 1s2, 2s2, 2p6. Perfect. And then 3s1. But what happens? We remove an electron. So you always remove the electron from the last sublevel. However, I need the, what color? Black. However, captain. Gonna make it bigger than the whole thing. However, when it ends with D, subshell, we remove electrons from the nearest S. So let's take an example, vanadium, V, which is what? Which has an atomic number of 23, and where is it? V, and has a mass number of 50. Perfect. Let's do its regular configuration, which is what? Which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d3. Perfect. But now, this is bugging me. But now we want vanadium 2 plus. What did we say? We said when it ends with AD subshell, what do? We have to go to the nearest s, and we will remove the electrons from it. So you will remove the electrons from this. So now its configuration is what? 1s2, 2s2, 2p6, 3s2, 3p6, and 3d3. Very, like, pretty much all of it. Now, this was the thing I was saying, where you have an equation in physics. Do you remember Coulomb's law? F is equal to k q1 q2 over r squared. Well, in chemistry, they want to be unique. They want to use the same equation, but they want to be unique. So they said that energy is equal to k q1 q2 over r. So what does this mean? This means E is directly proportional to the charges and inversely proportional to the radius of the in between the electron and the nucleus. That means as the charges increase, energy increases. But if the radius increased, then what happens to the energy? It would decrease. Okay, so now we reach what? We reach a small equation. It's a bit, I don't think it's coming, but it's nice to know that the energy of photons is what? The energy of photons is the binding energy in addition to the kinetic energy. You just need to know like this. You can find the binding energy and kinetic energy and add them. Now here is the very, very last concept, and then I can finish this video, and then I can post it, and I can start maybe a new video. This concept is PES. No, not like PES in business and economics. This PES is not price elasticity of supply. No, this PES is the photo electron spectroscopy. Perfect. What does this mean? This means we have what? We have a graph, first of all. You can say, okay, because it's PES, it reminds me of business or economics, so I'll draw a graph. Perfect. You draw a graph. Now what do we say? We say that on the x-axis of the graph, we have the binding energy. What is the binding energy? It's in megajoules per mole. The binding energy is the energy required to overcome the attractive forces between an electron and the nucleus of an atom. Okay, so binding energy is the energy required to overcome or conquer the attractive forces between an electron and the nucleus of an atom. And what do we have to the side? To the side, we have the relative number of electrons. Let's take an example. Let me draw an example graph. Let's say we have this peak over here, and this is 2, right? So this is 4, this is 6, for example, right? This is our graph. This is at 84. Okay, the energy is at 84. Then we have a large space. Then we have another one, which is at 2. And then another one, which is at 6, right? Now let's say this is 8 and 5. طيب, what do these values 84, 8 and 5 represent? Very simply, they represent the binding energy required to overcome the attractive forces. That means from this over here, which for now we will say it's the last energy level, it's the easiest. It requires the less energy to remove what? To remove the electron from the last energy level. Whereas compared to this one over here, this one requires so much more energy than these two over here. Okay? So the closer it is to the initial point, this is how I take it. The closer it is to the initial point, that means the closer it is to the nucleus. And the closer it is to the nucleus, that means the stronger the force of attraction. The stronger the force of attraction, that means what? That means we will need more energy required. Now what do? Let us do the configuration. This is first of all 2, so we always start with 1s2. What comes after 1s2? S. And then finally, last but not least, 2. And then last but not least, it's 2p6. So what is this element? In your opinion, what's this element that has a configuration of 1s2? And it's an atom, by the way, not an electron. Not an ion, my bad. 1s2, 2s2, and 2p6 has how many electrons in total? 10 electrons in total. So we will look. We'll see which has an atomic number of 10. It is neon. So this is what this is, neon atom. Perfect. Amazing. We finished this video. Thank you guys for watching. I really do hope you enjoyed and understood. And have a wonderful day. Let me just get back to the top because I like to just go back here. Here we go. Thank you guys for watching. I hope you enjoyed and have a wonderful day.